So the last product we're going to talk about today is the cross product. And the cross product is special because it only works for vectors in R3. So it's only for vectors I use that symbol for in, it's the mathematical symbol, and R3 just meaning three-dimensional vectors. And it follows a kind of weird rule. So let's say we have two vectors, A, B, C, cross a vector D, E, F. And one thing is we're actually really going to want to use that standard basis notation here. So we can really think about this as AI plus BJ plus CK cross DI plus EJ plus FK. And the rule we're going to use is we're going to take the determinant of a 3x3 matrix. So I'll explain what we mean by that. So we're going to take the determinant of a matrix whose first row is IJK, whose second row is the first vector we have, ABC, and whose third row is the second vector we have. And order is going to matter here. I'll let you experiment with that a little bit. Well, we'll see an example here. So if you don't remember how to take the determinant of a three-dimensional or of 3x3 matrix, there's a little bit of a more visual way to do this. So what we're going to do is we're going to repeat the first and second column here. There's a reason we're doing this. Then we have B and E. And what we're going to do is we're going to kind of multiply across these three diagonals. And that's going to get us three numbers. That's going to get us B, F, I. The reason I'm leaving the I at the end is, remember, this is not just a number, this is a standard basis vector. So we kind of want to leave it at the end. Plus CDJ plus AEK. And then we're going to actually subtract going in the other direction. So we'll have three lines going this. Oh, that was a horrible line. Undo. Okay, let's try that again. We'll have three lines going like this. And we're going to subtract those values. So I'll have minus BDK minus CEI and minus AFJ. And then at this point, you might need to add a plus sign there just to remind yourself that there is an invisible plus sign here. Then we go ahead and combine like terms, and we'll get something. We'll look at our I terms. What do we have? Well, we'll have BF minus CEI plus the J terms. We'll have CD minus AFJ plus AE minus BDK. So that's a really complicated formula. It will take a little bit of time to get used to this, but with some practice, which is why we're here, it should become second nature. So let's do an example. Let's start with a kind of interesting motivating example. Let's take the vector I cross the vector j. If you remember, I dot j, and I should point out, these are we have to be in R3 whenever we're talking about the cross product. But if we remember, I dot j ended up equaling 0 because they're orthogonal. So what happens if we do I cross j? Well, it's going to be the determinant of a 3 by 3 matrix. So we'll have I, j, k in our first row. I is really the same as 1, 0, 0. So we'll have 1, 0, 0 here. And then we'll have 0, 1, 0 for j. We'll add in the second two rows just as a little helpful guide. Once you get very practiced with the cross product, you can skip that step. I would not recommend skipping that step until you are very, very, very comfortable. So we'll do this. We'll look at these 3 diagonal lines. That one, it did go through that one, I promise. And what we'll notice is that a lot of these ended up being 0. We had 0i, we had 0j, but we had 1k. Going in the other direction, everything had a 0 in it. We had 0 times 0, we had 1 times 0, we had 0 times 1. So it turns out that our answer is 1k. And one thing, this seems interesting in a number of ways. One way this is interesting is that k is orthogonal to I and j. And this is going to end up being a pattern. So there's one example. Let's do another simple example, and then we'll do one with some more interesting numbers. So next example, let's try j cross I. And, you know, you might expect this to be the same answer. With the dot products, we never even asked what happens if you change the order. And part of the reason is because when we're talking about the dot product, it's all calculated using addition and multiplication, each of which are commutative. In this case, we have some subtraction going on. So we should at least think about the fact, is this commutative or not? What does changing the order do? So now we're doing j cross I, so we'll put our first vector, which is 0, 1, 0, in the first row, and then 1, 0, 0 in the second row. Add in a couple extra columns, and let's see what we get. So if we go here, we'll notice that all of these ended up being 0. We had 1 times 0, 0 times 1, and 0 times 0. But if we go the other direction, we get a few zeros. We get 0 times 0, 0 times 0, but we also get 1 times 1k. And remember, we subtract all the ones that we're doing in this direction. So we're going to end up getting negative 1k here, which you should notice is not the same as positive 1k. Those are two different numbers. So we see that I cross j does not equal j cross I. All right, so we see that I cross j does not equal j cross I. What we saw specifically, though, was that we ended up getting the negative answer. So in fact, we'll say, in fact, and I'll write more generally here, A cross B equals negative B cross A. And that would, you would need to show that's true, but I'm just going to tell you right now that is true. Okay, so we've done a little bit of practice with our cross product. Let's do one example that isn't just standard base or sectors. How about 3, 0, 4 cross 2, 1, 0. So we're going to end up, we'll draw our 3 by 3 matrix. This time we'll have actually interesting numbers. So we'll have 3, 0, 4, and 2, 1, 0. Remember, we'll repeat that last column, or the first two columns, I mean. And then we'll draw our lines for the addition direction. We'll see that here we have 0i plus 8j plus 3k. And then in the other direction, we'll have minus 0k minus 4i minus 3j. Oh, sorry, minus 0j. There was a 0 there. Okay, which means that our final answer is going to end up being, well, for I, we'll have 0 minus 4. That's going to be negative 4i. For j, we'll have 8 minus 0, so that'll just be plus 8j. And then we'll have plus 3k. So what we would like to do is see, do we still get this pattern where both of these vectors are orthogonal? So this might take a little bit, but let's go ahead and see what we can do. So we'll have our nice coordinate axes. So we'll have x, y, z. I'm going to need to be a little careful how I draw these. We'll have, first, we'll have the vector 3, 0, 4. So we'll have 1, 2, 3. I did make sure there were some zeros in here so that it was a little easier to draw. So we'll have one vector going like this. Oops, let's try to get that a little better. We'll have another vector, which is 2, 1, 0. So let's go back to our black pen. We'll have 2, 1, 0. So we'll need to have the 1 there. So we'll have one vector going like this. And then our next vector is kind of really big. So this one will be negative 4i, so we'll need to have a little bit in the negative direction. So we'll have 1, 2, 3, 4. We'll have 8j, 1, 2, 3, 4, 5, 6, 7, 8. And 3k. So what will that look like? We'll have negative 4. And then 3k. Just draw my little box to help me keep this straight. And we'll have this vector going off in this direction. And again, It's kind of hard to tell when we're in multiple dimensions like this, but in fact, that is going to be perpendicular to the red and blue vectors. So, and you can kind of see it a little bit. So, yeah, just like one of the key facts of the dot product is that if you take the dot product, you get 0. A key fact here is that the vector A cross B is orthogonal to A. I'm going to draw some things. I don't think I've been doing that good. You should be careful when you're writing vectors. Make sure you're noting their vectors in some way. I think it's good to put a little arrow on top. So I should be doing that. It's orthogonal to A and to B. So should probably change that up here too. Anyhow, so we've kind of learned two interesting things about the cross product here. We learned that, first of all, it's not commutative. When you switch the order, you get the negative of your original answer. And we've learned that the cross product gives you a number that's orthogonal, or gives you a vector that's orthogonal to both of your starting vectors. Those are kind of two important things here.